survey where the goal is to get rest-frame optical spectra for 1,500 galaxies, masses ranging from 10 to the 9.5 to 10 to the 9 to 10 to 11.5, and star formation rates anywhere between 1 to 1,000 solar masses per year. And actually, we are now complete. We did reach our target, and we have 1,500 galaxies. So for instance, just to give you a flavor, here's an example
So we have rest frame optical spectra in multiple bands, and we've combined that with the existing multi-band photometry ranging from rest frame UV down to the IR. So an example for a star forming in a quiescent galaxy in our survey. And really the power of this survey is to combine these rest frame optical spectra with the existing multi-band photometry for a large sample of galaxies to really start probing properties of galaxies at redshifts, 1, 2, 3. In particular, one of the things we can do with this is to examine the kinematic structures of these galaxies. So to study that, we went ahead and selected a sample of galaxies where we had both coverage of H alpha and H beta. We went ahead and said, all right, let's do the kinematics with the H alpha line. And for the majority of these galaxies, we also had H beta detected. We also went ahead and said we must have structural parameters from the Candel's F160 imaging. The challenge of doing kinematics with MOSFIRE is that, generally speaking, you're going to have randomly aligned slits relative to the galaxy major axes. And this is particularly the way the MOSDEF survey was targeted, wasn't really selecting to get the galaxy major axes aligned with the slits. So we needed to come up with something else rather than just a straightforward aligned slit analysis to get the kinematic information for these galaxies. So what we went ahead and did and made simple 3D spatial models of these galaxies where we used the structural parameters from the Candel's imaging to find out how much of the galaxy is falling within the slit and at what orientation. And we're able to fold in a rotation velocity curve and a constant velocity dispersion, and then include the seeing conditions to basically to match what we would actually observe. So for instance, you can see, input a velocity map. So this is sort of already projected from the 3D distribution of the model. We have an intensity map, and then the resulting observed 2D emission line model for the case where maybe a galaxy is aligned with a slit. And so this model is able to naturally take into account the cases where, say, you've misaligned the major axis with the slit, and you've included velocity dispersion. So it already incorporates the reduction of the rotation signal that you'd get under these observational conditions. Okay, so for an example for one of our objects, we start with the Candel's imaging. We start with the 2D H alpha emission line. By convolving the Candel's imaging to match MOSFIRE seeing, you have a really good idea of how much of the galaxy is falling within the slit. We can then use this sort of model, these models to create a resulting 2D emission line model that then does match our incorporated rotation signal, and then to back that out to try to get the intrinsic rotation velocity and velocity dispersion. So we see a detected rotation signal, all right, velocity shear, I will give you that caveat, for only 20% of our sample, largely because a lot of our sample are smaller than the seeing limit. But for this 20% of the sample where we do detect what we interpret as a rotation signal, we find an average V over sigma of about 2. All right. But we'd like to do something with the kinematic information for the rest of our sample as well. And so the question is, are these galaxies where we're not seeing rotation signal, are they disks or could they be disks? Well, there's reasons to believe that they could. So work that Sarah Newman did with AO, you could in fact just have rotation signal hiding because it's been smeared out from seeing conditions. So from the SINS survey, they have both seeing limited kinematics and AO kinematics, where it's not very clear under seeing limited conditions, but it does seem to have a much more ordered velocity field under AO conditions. Additionally, for the MOSDEF survey, we have the slit misalignment, which could further get rid of an observable rotation signal. So for the case where we don't detect rotation, we go ahead and try to use the same set of models to say, okay, let's back out some average kinematic information. So we take the observed 1D velocity information from the line width. We take these kinematic models, which includes how much of the galaxy is lying within the slit, which includes inclination effects,
Now, we have to assume a ratio of V over sigma, and so we'll say, okay, maybe these galaxies are similar to the galaxies where we did see a rotation signal. And I'll argue later that's actually not a bad assumption. And so we use this to get out a combination of the rotation velocity and the velocity dispersion. So one of the first things we can do with this is try to say, let's measure dynamical masses and compare them to baryonic masses. So we take the combination of the rotation velocity and the velocity dispersion, and I can talk about this more later if you'd like to speak with me in person, and compare that derived dynamical masses with baryonic masses, which we get stellar masses from SED fitting. And what we do is we go ahead and take Balmer absorption and dust-corrected H-alpha star formation rates to try to infer the gas mass. So here showing the baryonic mass versus the dynamical mass for the galaxies where we did detect, a rotation signal. And as Reinhardt mentioned, yeah, it is uncomfortably close to the not much room for dark matter. And so then throwing in the points where we didn't detect a rotation signal, but instead using that average V over sigma to say, okay, maybe an individual galaxy dynamical mass might be a little bit wrong, but for everyone maybe you get low, you get one high. So on average, these galaxies do agree well with the cases where we did detect a rotation signal. What we can also do is say, well, what if we've selected AGN? So not broadline AGN, but if AGN satisfies the rest of the criteria, what might we find? Well, in this case, maybe we're actually probing the host galaxy kinematics because they do seem to agree pretty well with the galaxies where we selected just star-forming host galaxies. Okay, but could we actually do something and separately measure the average amount of rotation to velocity dispersion for the galaxies where we didn't detect rotation? I'm going to argue on average, yes. Sure, not for an individual galaxy because you just don't have that information. But if we'd said, all right, let's assume there's no velocity dispersion at all, we see a definite trend with axis ratio, so edge-on galaxies to face-on galaxies, and then looking at the difference between the dynamical and baryonic masses, where you're basically overcorrecting for inclination if you've excluded any velocity dispersion. So just basically, in an average sense, walking through and saying, how do we get rid of this trend? How do we properly account for inclination? And if you basically walk through that, you get the same value of V over sigma as for the cases, as the median value for where we did detect rotation. So that this assumption at the beginning, at least in an average statistical sense, was a reasonable assumption. Okay, so what we can do beyond that is say, well, maybe what does this tell us about possible galaxy properties? So what KMOS 3D has done, wonderful work. They see evidence for disk settling with, so looking at a decreasing trend of V over sigma, the amount of rotational support, with increasing H-alpha specific star formation rate, which you would expect to correlate with gas fraction. And we actually find good agreement with that. And then also, same trend with the galaxies where we hadn't immediately detected rotation if we've now done that in two bins. So briefly, we also then might look at a modified Tully-Fisher relation, so this SO5 indicator combining both rotation velocity and velocity dispersion. And so here I'm looking at the baryonic mass to try to exclude any evolution of gas fraction. And so compared to Susan Cassin's work at redshift 0.2, we were seeing at fixed baryonic mass a smaller amount of a smaller SO5, which might indicate a smaller dark matter fraction, which you might naturally expect because on average these galaxies are smaller at higher redshift, and so they might be probing less far out into the dark matter halo. But a big question for all of this is this ionized gas kinematics actually tracing what we think it is? Are we actually recovering dynamical masses? Are we actually, really understanding this in the context of what it is? And so a way to look at this is by looking at mock observations of simulated galaxies, particularly cosmological simulations. The massifier simulations are well suited to this. Excellent spatial resolution, excellent mass resolution, realistic galaxies, realistic treatment of dust. So being able to go ahead and say, let's look at mock photometry and mock spectra to try to say what sizes, what masses are we recovering, and what kinematics are we recovering. And so be also especially looking at this from multiple orientations, so saying how might inclination affect these measurements. So, more or less as you might expect, artificially redshifting it, including PSF, adding some noise, and looking at multiple projections in multiple filters. And so the really short preliminary results I want to share with you is let's just ask, how do the sizes compare? So if we measure the sizes using GalFit in a rest frame band and then compare the intrinsic mass sizes, they're definitely way too large. You are overestimating the galaxy sizes. Now, this is established before. Daniel Zamora tried to use a mass to light ratio correction to try to then include for effects of age, dust, and metallicity. And so if we tried to use his prescription, we still get sizes that are too large, but they are on average closer. But this would have implications for saying, okay, so maybe your simulations match observed galaxies in size. Well, are we really comparing the right sizes? And so I think this is still very preliminary work, and I'd be happy to talk with you more about this, but I am out. So I just point out that in the future we will have data releases. We have redshifts released on the following website, but we will have the full data release from the MOSDEF survey in the future, so stay tuned for that.
Thanks. A couple very short questions. So one, typically higher specific star formation rate systems are physically smaller, and that makes V over sigma harder to measure. What are your thoughts about that first? And then the second is, where's this overestimation of size coming from? Is it dust in the central parts being optically thick?
I think that might be definitely part of it. So, okay, let me address your second question first. I think dust is definitely a possibility, but not for everything. There were some of these things. One of these two is definitely fairly quiescent, and right, I don't think there's that much dust, but it's, yeah, no, I think this is a very interesting question, and I think there's a lot of work to be done in a number of different simulations and different questions to be asked. As far as the size for V over sigma, I 100% agree, but for the cases where I think that so we didn't necessarily track that down as well in our data because honestly, even getting rotation signal at all for some of the seeing limited was challenging. But I think partially with Raymond Simon's work, he was looking and saying, yeah, they were seeing some similar things, and in these cases, they were able to recover, reasonable rotation velocities, and so maybe this is a real signal. So.
Yeah, I have also a similar question about the kinematics. We have tried sort of hard to get sensible rotation curves out of these model galaxies, and thus far it's been really challenging, even just getting a kinematic signature of a flattened rotating disk out of it. And I'm just wondering, what do you think about that? Are you seeing similar things in Bayer?
So for massive fire, we haven't quite gotten to doing the Mach spectra yet. Just making sure I had all my ducks in a row for getting the Mach photometry. But yeah, no, I think that's an interesting question. And so it would be interesting to see what the different simulations predict as far as stars and gas. But even if you were to step back and say, well, okay, maybe the simulations show one thing or another, and maybe that means the physics is right or not. If you said, well, let's assume this was the input, let's assume that is the real universe, trying to ask the question of are we recovering what we do or don't see. I think there's a lot of work to be done. This is sort of an interesting thing, and you are absolutely right. It's very challenging. So it's maybe we could talk more later.
Okay, if there are no further questions, let's thank Sedona again. And now we have Intae Jung, evidence for the suppression of star formation in the center of massive galaxies at Z of something.
Hello, everybody. My name is Intae Jung, a graduate student from University of Texas at Austin, and my advisor is Steve Finkelstein, and I'm in collaboration with the Candace team for this project, including Abhishai and Yulu in this room. First, I'm very much glad that I'm able to introduce my talk in this wonderful meeting, and then I think that most of you are new to my project. So I'm going to skip this motivation